Imagine standing on the shores of an alien lake where the waves aren't made of water, but liquid methane, flowing like honey at nearly 300 degrees below zero. This isn't science fiction. This is Titan, Saturn's largest moon, where NASA scientists have just discovered something that could revolutionize our understanding of life itself. In 2025, researchers announced that these frozen hydrocarbon seas might naturally create the building blocks of primitive cells, opening a breathtaking possibility. What if evolution took an entirely different path on this distant world? The story begins in the most unlikely place for life as we know it. Titan exists in a realm so cold that water becomes harder than granite. Yet its surface hosts vast lakes and seas of liquid methane and ethane that dwarf the Great Lakes. When the Cassini spacecraft first revealed these alien waters in 2004, scientists initially thought they had found a frozen wasteland. But recent discoveries have shattered that assumption, revealing an active world where methane rain carves riverbeds, seasonal storms reshape coastlines, and complex organic chemistry unfolds in ways that mirror the earliest stages of life on Earth. The breakthrough came when NASA researchers realized that Titan's methane lakes could spontaneously create vesicles, tiny bubble-like structures that act like primitive cell walls. These aren't random formations, but the result of elegant chemistry involving amphiphiles, molecules with both water-loving and water-repelling parts. On Earth, similar molecules naturally assemble into the membranes that surround every living cell. But on Titan, this process unfolds in liquid hydrocarbons instead of water. When methane raindrops strike the lake surface, they splash and create aerosols that carry these crucial molecules into the atmosphere, where they can form stable protocells as they fall back down. This discovery builds on our understanding of extremophiles, Earth's most resilient organisms that thrive in conditions once thought impossible for life. Deep in our planet's ocean floors, methanotrophic bacteria have evolved to consume methane as their primary energy source, converting it into complex organic compounds through sophisticated biochemical pathways. These remarkable organisms, belonging to groups like Methylocyanus trichosporium, have developed enzymes that remain active in extreme temperatures and chemical conditions, suggesting that methane-based metabolism isn't just possible, it's already proven on Earth. But Titan's potential life would face evolutionary pressures unlike anything on our planet. At -292 degrees Fahrenheit, traditional water-based biochemistry becomes impossible, forcing any hypothetical organisms to develop entirely novel metabolic strategies. The available energy sources would be radically different too. Instead of sunlight or chemical reactions involving oxygen, Titanian life might harness the energy from hydrocarbon reactions, or the complex organic chemistry occurring in the moon's dense, nitrogen-rich atmosphere. Recent research into anaerobic methane-oxidizing archaea provides fascinating insights into how such organisms might evolve. These Earth-based microbes, known as ANME, have developed intricate partnerships with sulfate-reducing bacteria, creating syntrophic relationships where one organism's waste becomes another's fuel. On Titan, similar evolutionary partnerships could emerge, but instead of processing sulfates, these alien organisms might metabolize the abundant ethane, propane, and complex organic molecules that rain from the sky. The evolutionary timeline for such life would unfold across geological epochs. Early protocells might begin as simple vesicles floating in methane lakes, gradually developing more sophisticated membranes, capable of regulating their internal chemistry. Over millions of years, natural selection would favor organisms that could better exploit Titan's unique resources, perhaps developing specialized organelles for processing different hydrocarbons, or evolving complex communication systems through chemical signaling in the dense atmosphere. These hypothetical organisms might eventually develop remarkable adaptations we can barely imagine. Some could become methane photosynthesizers, using the dim sunlight that filters through Titan's hazy atmosphere to convert atmospheric methane into more complex molecules. Others might evolve into deep lake specialists, thriving in the lightless depths where they process the organic compounds that settle from above like an endless rain of nutrients. Still others could become atmospheric floaters, living their entire lives in the dense nitrogen sky, feeding on the complex organic aerosols that form through photochemical reactions. The energy budgets for such life would be fundamentally different from Earth's biosphere. While recent studies suggest that Titan could support only a tiny amount of biomass, perhaps equivalent to just a few pounds across the entire moon, this doesn't preclude the existence of highly specialized, slow-growing organisms perfectly adapted to their energy-poor environment. These creatures might have metabolisms thousands of times slower than Earth life, existing in a kind of biological suspended animation that unfolds across centuries rather than seasons. One of the most intriguing possibilities involves the moon's dual nature. Titan possesses both surface hydrocarbon lakes and a subsurface ocean of liquid water. Cometary impacts could occasionally breach the ice shell, creating temporary connections between these two completely different chemical environments. Evolution might eventually produce organisms capable of surviving in both realms, essentially becoming interplanetary amphibians that bridge two entirely different biochemistries. The reproductive strategies of Titanian life could be equally alien. Instead of DNA, these organisms might use polymer chains based on nitrogen and phosphorus compounds that remain stable in liquid methane. Their genetic code could be written in the language of hydrocarbon chemistry, with information stored in the precise arrangements of carbon chain molecules. Reproduction might occur through vesicle budding, where parent organisms literally split off portions of themselves that carry both genetic material and the essential biochemical machinery needed for survival. As these ecosystems matured over deep time, complex food webs could emerge. Primary producers might convert atmospheric methane and ethane into organic compounds, supporting consumers that specialize in breaking down different types of hydrocarbon chains. Predatory organisms could evolve chemical warfare capabilities, producing toxic compounds that dissolve competitors' membranes or interfere with their methane processing enzymes. The entire ecosystem would pulse with Titan's 29-year seasonal cycle as organisms adapt to the dramatic changes in temperature and chemistry that occur as Saturn's system orbits the distant sun. The implications of discovering such life would fundamentally transform our understanding of evolution itself. Life on Titan would represent a completely independent genesis, what scientists call abiogenesis, proving that the emergence of life isn't a singular cosmic accident, but potentially a common occurrence wherever the right chemical conditions exist. This alien biochemistry would expand the boundaries of the habitable zone far beyond what we currently imagine, suggesting that life might thrive in the methane lakes of other moons, the hydrocarbon seas of distant exoplanets, or even in chemical environments that we haven't yet discovered. Perhaps most remarkably, studying Titanian evolution could reveal fundamental principles about life that transcend any particular biochemistry. The evolutionary pressures that shape organisms, the need to gather energy, reproduce, and adapt to changing environments, might produce convergent solutions even in radically different chemical contexts. We might discover that certain biological strategies, like cooperation, competition, and specialization, represent universal features of evolution, regardless of whether life is based on water and carbon or methane and complex organics. The story of life in Titan's methane lakes remains unwritten, awaiting future missions that could confirm whether these frozen seas truly harbor alien biochemistries. But the scientific foundation for such possibilities grows stronger each year, as researchers uncover new mechanisms for protocell formation, discover ever more extreme organisms on Earth, and develop sophisticated models of how evolution might unfold under conditions completely unlike our own planet. Whether or not we eventually find microbial swimmers in those distant hydrocarbon seas, the very possibility forces us to confront profound questions about the nature of life, the boundaries of evolution, and our place in a cosmos that may be far more alive than we ever dared imagine.